CPUs provide advanced mechanisms like pipelining and memory management. RISC-V is designed to support pipelined execution. Each stage performs an operation, hands the result to the next stage, and accepts from its previous stage the next instruction. This pipeline diagram shows how several instructions proceed through the pipeline. In many cases, the pipeline can start a new instruction on every clock cycle and finish one every cycle. Three types of situation complicate the control of the pipeline. A structural hazard occurs when two different instructions try to use the pipeline resource at the same time. The PC update logic is an example of added hardware used to avoid structural hazards. Hazards would occur on many instructions if the ALU used for instruction operands were also used to update the PC. Adding separate update logic avoids the creation of these hazards. Another type of complication is a data dependency between two instructions. In this case, the first instruction writes to register X28 while the next instruction reads that same register. Whether the situation becomes a data hazard depends on the microarchitecture. Some types of data hazards can be avoided by providing extra bypass hardware to make the value available. Branches can also create control hazards. An unconditional branch is simple. The opcode indicates that a new value will be provided to the PC. A conditional branch, on the other hand, is not known until the condition is evaluated. In this example, a BLT instruction is taken on a basic 5-stage pipeline. The subsequent add-I is fetched, followed by an add instruction. When the BLT is evaluated and the CPU knows that the branch will be taken, the add-I and add are canceled and treated as no-ops. Memory management provides hardware assist to help the operating system organize its use of memory. A simple approach to compiling instruction would cause problems when multiple programs share the CPU. Directly using effective addresses would fix the location of the program in memory. Each program would have to be compiled into a given range of addresses that couldn't be used by other programs. Memory management mechanisms allow the CPU to decouple effective addresses from the locations of programs in memory. Memory is divided into pages. Page sizes vary from architecture to architecture, but a size of 1K to 4K words is typical. A page is the unit of organization in memory management. The effective address provides a logical address within the idealized program. Memory management translates the logical address into a physical address for the memory system. The Memory Management Unit, or MMU, manages address translation. A page table describes the mapping from logical to physical pages. A fully populated page table can be very large. Several techniques can be used to reduce the size of the page table, particularly when not all the address space is used for a given program. The address within a page is described as a page offset in the low-order bits that can be directly copied to the physical address. The high-order bits give a page number that's translated using the page table. The translated page and offset can be easily combined by concatenation to give the physical address. MMUs can also provide memory protection to implement permissions to access memory locations. Here, Program 1 is not allowed to access the memory occupied by Program 2. A program may also try to access operating system locations for which it doesn't have permission. The MMU and page table can record access privileges on a page-by-page basis and check each access for validity. An invalid access results in a trap to the operating system. The operating system may want to avoid putting all of the program into memory at once. Some of the pages in the program may be used in later stages or not at all. The physical memory may not have room to simultaneously hold all of the active pages. Virtual memory combines hardware and software mechanisms to allow on-demand paging into physical memory. The page table is enhanced to include information about whether each page currently resides in memory. If a page specified in a logical address is resident, the translation process proceeds normally. If the requested page is not present, hardware generates a page fault. The page fault is handled by the operating system software. The OS uses tables to determine the location of the page in storage, such as a solid-state disk. It then performs an I/O operation to transfer the page from storage to memory. Once the page table has been updated, the CPU restarts the memory request, which can take advantage of the page's residence in memory. RISC-V uses privilege modes for memory management. The supervisor mode is primarily used for memory management and virtual memory functions. Control and status registers are used to describe the state of privileged operations. Thanks for watching.